Hello and welcome to the third and final part of our series on structural analysis with solid steel parametric for SolidWorks. In the videos we show different methods to perform static calculations after the design has been created with solid steel parametric, and in today's video it's even done directly during the design. We'll look at two examples to show how easy it is to incorporate structural analysis into the design if you have the right tools. In the first example I used solid steel to draw two columns and wind bracing made of L-shaped profiles. So far without any details, because how should I know the dimensions for correct detailing? Fortunately there is software with which we can quickly answer such questions. The software, or more correctly software collection that I would like to introduce today, is called Stahl 2000, contains a whole series of practical tools and is made by Cleach. The tools are easy to operate and thus allows us to create a structural analysis parallel to the design. I had estimated the L profiles with 60 by 60 by 6 mm. Let's check if this was a good choice. The Stahl 2000 launcher shows us an overview of the individual apps. The icons make it easy to find your way around, and wall bracing is the right tool for my first calculation. Here we can now select in the first step whether we want to calculate a K-brace, a double, a multi-level, or as in our case a simple cross brace. A few parameters must be specified, of course, such as the width and height of our bracing and also a horizontal load. I'll take 10 kN. Clicking on the calculator icon starts the calculations, but first we assign a position number for our calculation. Another query appears and we confirm with yes that Stahl 2000 should perform the complete analysis and not only calculate the internal forces. In the next window I'm shown for which members the calculation is possible. Since we are just interested in the tension diagonal for this wind bracing, only one member is available for selection here. Now I can also indicate that I have just used an L section in solid steel, but it would also be possible to calculate round bars or threaded rods. In the list I select the appropriate 60 by 60 by 6 mm. With the next window I got a screw selection. Here I specify the diameter, the grade and the number of screws. Geometrical factors such as the distance to the beginning or the bottom edge of the profile or the distance between the screws are specified. Remember this information, we will need it later. Immediately after confirming the entries we get the first result of the calculations displayed. Everything is clearly smaller than 1 and thus on the safe side. Let's now have a look at the detailed calculations. The PDF is generated at the push of a button. Here we see on the first page the system sketch with the dimensions, the support forces and the member forces in the individual members. On the second page we find the dimensioning of the diagonals. In the upper part we find the calculations concerning the L profile. By the way, here with a utilization factor of 0.32 everything is perfectly fine. In the lower section we find the dimensioning of the bolted connection, and with the results here we see that shearing with a value of 0.33 is prevented, and also the hole reveal has been well chosen, since here a value of 0.37 is obtained. Our bracing is now fully dimensioned and we know that it can be used in these dimensions without any problems. This took maybe 3 minutes in real time and with my explanations, but with a little practice you can easily do it in 1 to 2 minutes. Good, we have finished dimensioning the wind bracing. The geometry of the gusset plate results by itself when we enter the parameters of the bolting and a few distances in solid steel. These are the values for which I just said that we have to remember then. Or we can of course also read these values in the PDF output by Stahl 2000. Since some viewers may not know solid steel yet, I will briefly show how to add bolts. To do this we click on Assemble in the bolt section and then select an M16 bolt to match our calculations. We also select the standard set, that is to add washers and nut automatically. Another click on the green tick and the selected connection also appears in the preview. Now I save the entire connection under any name and can use it again and again. This now with the other gussets in fast forward. We do not need to calculate separately that the gusset plates can withstand the load, because the critical geometries are exactly the same as for the diagonals, only with greater material thickness, so we are on the safe side. The question if the welded connection of the gusset plate to the support is also able to withstand the load cannot be answered with the same degree of certainty. To answer this question, let's start the next app from Stahl 2000, which knows exactly how to do this. The app Connections can calculate different kinds of connections. We select here the tab for the gusset plate. As the first value, we enter the tensile force we just calculated, including the safety factor. This was the first value on the PDF's second page and was 21.21 kN. Further details are then the angles of the tensile force, details of the holes, how much clearance we want to allow, and of course the length and thickness of the welds. We get the results immediately after clicking on the calculator and assigning an item number. As you can see, the calculation of the welded connection between the gusset plate and the beam has shown that the utilization factor of 0.11 is clearly on the safe side, and the design in this way is no problem at all. Having solved the first case, we now move on to the second example, a frame with ribs and an end plate connection. Something like this is quickly drawn with Solid Steel Parametric for SolidWorks. Just look over my shoulder in the fast forward, and if you want to know more about it, you can find links to videos where this is shown in detail in the video description. Alright, that looks like a frame to me. Everything is complete with end plates bolted in place, the ribs sitting where they should, the profiles were automatically and correctly shortened, and welded assemblies were also automatically generated. With the profiles used, this is a very slender construction. Whether the HEA 180 beam size shows were a good choice, we will find out again with the help of Stahl 2000. The app 2D framework is a good choice to dimension our frame. The principle here is exactly the same as in all Stahl 2000 apps. The users reach their goal with logical sequence specifications. Step 1 is then of course that I specify from which profiles my frame is to be built. The selection is quick via the menu, and I shows of course the HEA 180 exactly as in the CAD drawing. In the second tab we define the static system. The input for this is done via a table. This looks complicated at first, but it simply corresponds to the use of a coordinate system and is very practical. For a better understanding, I'll show a sketch that makes it clearer what I'm actually doing. Let's start with member 1, our first support. This has a length of 0 and a height of 3.5 meters. The cross-section is our profile 1 that we had just defined, and the member starts from node 1 and ends at node 2. For example, if the support was slanted, I would have simply given a measurement for the length. You can see the result in the sketch. But back to our frame. We continue with the horizontal beam, which I enter in the system as two half beams, each with a length of 2.25 meters and a height of 0 meters. So I get the node 3, for which I then get, for example, shear forces and moments in the center of the beam in the later calculation. The second support is still missing. It has a length of 0 meters again, and for the height I enter -3.5 this time, because the data are always interpreted from the last node. Now we have to specify which nodes are supported, and in our case these are nodes 1 and 5. We switch to the tab for the load cases. We will now create one combined load case for our example, but the app can also be used for the calculation of different load cases. We take a vertical uniform load of 15 kN per meter for the calculation, and this is then of course on the bars 2 and 3. In addition, we create a horizontal load that is applied to node 2. By clicking on additional outputs, we can select that stresses, field moments and displacements are also to be calculated. Then we start the calculation, define an item number again, and as usual with Stahl 2000, get the results immediately as a well-arranged PDF. On the first page we see our data entry. On the second page we can already see the largest occurring stress at member 4 with almost 20 kN per centimeter square, calculated without safety coefficients according to first order theory. Thus, without looking at the last page, we can already say that the selected HEA 180 beam was too small. On the last page it becomes even clearer when you look at the deformations, because you can see that the supports bend almost 5 cm in the horizontal direction, which is no longer acceptable. So we need a larger beam and we have to recalculate the design again. This sounds like a lot of work, but with Stahl 2000 it is a simple task. To do this we simply switch back to the first tab, select a larger profile, I'll take an HEA 240 and recalculate everything on the fly. Looks good now. The highest occurring stress is now only 8.29 kN per centimeter square, and also the deformations are now only 1.4 cm and thus completely okay for the initial design. This was easy with Stahl 2000. Now it would still have to be proven that solid steel parametric can handle such changes just as flexibly. In this case, the parametric of solid steel now comes into full play. We select the menu item Beams on Lines and use the change function of the menu. Now we select the two profiles of the columns. The blue color indicates which profiles have been selected for modification, and the red color also indicates which additional components are affected by the changes to the profiles. In this case, these are ribs and end plates, which of course no longer fit when the profile cross-section changes. In the profile selection, we change the support from HEA 180 to the just calculated HEA 240. Immediately get a preview and confirm the change. We now change the upper beam in the same way to an HEA 240. Let's take a look at it up close. That doesn't look nice, it can't stay like that. Fortunately, there's the update button I press now, and that will then adjust the ribs and shorten the beams to fit. It takes a little moment. I use the time to tell that in the result the ribs were adjusted, but the end plates were not, or let's say not in the way we expected. Okay, that's it. The reason that end plates are not automatically adjusted is that it's not only the geometry of the parts that counts, but also many other parameters that were defined when the end plates were selected. So solid steel can't know if exactly these end plates should be kept or not. Now that we have to redefine the end plate anyway, we can also dimension it with the Stahl 2000 end plate app. As a first step, we have to enter the internal forces that we have just calculated during the design of the structure. Bending moment 77.48, shear force 73.97 and a normal force of 22.14 kN. In the Dimensions tab we select the desired type of end plate. In our case it is the first one in the list. We want to make a standard joint according to DAST and therefore click on Load Standard Joint. In the following selection menu we choose the HEA 240 profile with M24 screws, click on Apply, and we are back in the previous menu where all the required specifications are now complete. So we can start the calculations immediately, and again the result appears as a PDF directly after assigning the position number. On the first page the inputs are summarized. Let's have a look at page 2. Here we see the most critical value for mode 3, the screw failure, with an utilization of 0.99. This is indeed very close to 1, but still okay. All other values are uncritical. With this we have now very quickly discovered how we have to change the end plates in solid steel. Back in solid steel we go to the end plate menu, select change and then the end plate. We immediately see a preview as solid steel jumps directly to the size of the new source profile. Of course, only end plates that fit the 240 profile now appear in the selection menu, and we select the plate to fit the dimensioning we just did. This side is now finished. We now do the same on the opposite side. As you can see, the short hops into the Stahl 2000 apps are quite beneficial. They help to work with realistic dimensioning of the components at any stage of the designing process. That's it for today. Thanks for watching and please check back next time.